Scientists have poured decades into the search for alien life, scanning distant exoplanets and icy moons alike. Yet one frozen world keeps rewriting the rules. Europa was supposed to be a straightforward candidate, a hidden ocean teeming with Earth-like vents and familiar chemistry. But fresh 2026 data has shattered that picture. The life scientists now suspect might exist. There is nothing like the bustling ecosystems we once imagined. It is quieter, more isolated, and profoundly stranger, thriving in pockets of liquid trapped inside the ice itself, rather than the deep ocean we always pictured. Europa looks deceptively simple from orbit. On a moon nearly 3,000 kilometers wide, the surface is so smooth that craters larger than a few kilometers have been erased almost as soon as they form. This is no frozen graveyard. It is a self-healing marble, a violent planetary-scale recycling machine that constantly erases its own history to protect whatever lies beneath 29 kilometers of ice. That smoothness is the first clue that something active, something alive with possibility is at work below. To understand why this moon might harbor life at all, you have to see its place in the Jovian system. Europa is locked in a gravitational dance with Jupiter, Io, and Ganymede, a precise mathematical resonance where Ganymede orbits once for every 2 of Europa's and 4 of Io's. This forces its path into a permanent ellipse. The distance to Jupiter shifts constantly, stretching and squeezing the entire moon by 30 meters every few days. Tidal flexing turns the rocky interior into a friction furnace. The only reason a global ocean can remain liquid at minus 170 degrees Celsius on the surface. Without this gravitational battery, the water would have frozen solid billions of years ago. Life here would not need a star. It would need only the relentless pull of gravity itself. That internal heat must rise. And the journey it takes through the ice shell decides every chemical pathway that could support biology. High-resolution images reveal fractures called lineae, massive canyons and ridges that trace the stresses of tidal flexing in perfect cycloidal arcs. These cracks do not match the moon's current rotation. The outer ice shell is floating freely on the ocean below, spinning at its own pace in a state of non-synchronous rotation. Over millions of years, the shell has drifted, leaving a scarred map of past tidal forces. In places, the surface looks like a shattered jigsaw. Chaos terrains where warm ice plumes have risen, tilted massive blocks, and refrozen them into new positions. These zones are not random geological scars. They are windows into the dynamic engine that could be delivering nutrients to hidden habitats. The reddish-brown stains inside those cracks and chaos regions were long mysterious. Spectral data from Galileo and Earth-based telescopes now confirm they are salts, magnesium sulfate and sodium chloride, the same table salt that dominates Earth's oceans. A January 2026 detection of ammonia in these disturbed areas changed everything. Ammonia acts as a powerful antifreeze, lowering the freezing point so liquid can persist higher in the shell. It hints that the chemistry flowing through the ice is far more complex than a simple saltwater bath. Radiation from Jupiter's magnetosphere bombards these salts, turning them dark and rusty. But that same radiation also splits water molecules, leaving behind oxygen that could fuel aerobic metabolism deep below. For years, the debate raged over the ice shell's thickness. A thin shell would mean easy exchange with the surface. A thick one would seal the ocean off like a tomb. Late 2025 and early 2026 microwave data from Juno settled the argument. The shell is roughly 29 kilometers deep. This is no thin eggshell. It is a massive layered barrier. The top few kilometers are cold and rigid. Below that, the ice warms and flows in slow, convective currents. At first, this seemed like bad news for life. How could surface oxidants or organics ever reach the ocean? Then a new 2026 model proposed crustal delamination. Dense, nutrient-rich slabs of irradiated ice become heavier than their surroundings and slowly sink through the entire shell like a conveyor belt. No giant fissures needed, just a patient geological drip feed of chemistry straight into the liquid world below. Even more intriguing are the perched lakes and brine pockets trapped inside the shell itself. Warm plumes rise but stall before reaching the surface, forming isolated bodies of liquid miles above the main ocean. Shielded from Jupiter's lethal radiation, yet close enough to receive the sinking chemicals, these pockets may be the most promising habitats of all. Life would not have to endure the crushing pressure of a 100-kilometer deep ocean. It could exist in pressurized, chemically rich pockets, stable for millions of years, evolving in near-total isolation. If biology has taken hold on Europa, it might not be swimming in the abyss. It could be living inside the ice, in hidden aquifers we never thought to search. Beneath that shell lies an ocean, roughly 100 kilometers deep, containing twice the water of all Earth's oceans combined. For decades, models assumed magnesium sulfate dominated its chemistry. Updated 2026 analysis of yellowish surface patches reveals sodium chloride instead, suggesting seafloor interactions that mirror Earth's early oceans more closely than anyone expected. The water is likely slightly alkaline, stable enough for complex organics to persist. Global currents driven by rotation and uneven tidal heating circulate nutrients from pole to equator. Yet the biggest surprise is what is missing. New geophysical models show the rocky seafloor is geologically quiet. Tidal stresses at the mantle are only about 150 kilopascals, far below the 51 megapascals needed to fracture rock or sustain hydrothermal vents. The seafloor is a cold, stagnant desert of ancient silicate, locked in chemical equilibrium for hundreds of millions of years. No black smokers, no fresh mineral fuel, no Earth-style vent ecosystems. This forces a complete rethink of how life could survive. Without high-energy vents, any biosphere must rely entirely on the slow downward rain of oxidants and organics from the ice shell above. It would be a low-energy, sparse world, powered not by fiery chemistry, but by the patient trickle of radiation-processed material. Life here would be patient, slow metabolizing, perhaps using hydrogen peroxide or molecular oxygen as electron acceptors in ways no Earth microbe has mastered at scale. The very radiation that sterilizes the surface is the same process creating the chemical battery that could keep a shadow biosphere alive for billions of years. Europa's ocean is habitable, yet it may be starved in exactly the way we once thought would doom it. That paradox makes the possibility of life even stranger, more resilient, and more alien than any vent-based dream. The thin oxygen atmosphere is another piece of this puzzle. Jupiter's magnetosphere slams high-energy particles into the ice, breaking water into hydrogen that escapes and oxygen that stays trapped. Over time, some of that oxygen migrates downward through cracks and delaminating slabs. It is a built-in lung for the subsurface, turning the radiation hazard into a resource. Early 2026 observations also revealed a persistent haze of water vapor concentrated on the trailing hemisphere, not from explosive plumes but from steady sublimation. This haze is not dramatic. It is steady, measurable, and perfect for a spacecraft to sample. It carries hints of the ice chemistry, possibly even complex organics, straight from the interface where surface meets interior. Right now, the Europa Clipper is en route, having launched in late 2024 and scheduled for a critical Earth gravity assist in December 2026. Its ice-penetrating radar will map the shell in 3 dimensions, hunting for those perched lakes and brine pockets where life might actually hide. Its mass spectrometer will sniff the haze for molecules and isotopes, distinguishing surface radiation products from potential seafloor or biological signatures. The European JUICE mission will add gravity measurements during its Europa flybys, double-checking the shell's rigidity and the ocean's response to tides. Together they will test whether the chemistry we see is only geological or whether something living is already altering the balance. Planetary protection rules are strict. At mission's end, Clipper will plunge into Jupiter, incinerating any hitchhiking Earth microbes so the ocean remains untouched for whatever future explorers follow. Every new model, every updated dataset from 2026 keeps pointing to the same unsettling truth. Europa does not offer the easy, sunlit, vent-driven cradle we once hoped for. It offers something harder, quieter, and far more profound. A world where life would have to invent entirely new strategies for survival. Shielded inside an icy fortress, sustained by the slow drip of oxidants from a radiation-blasted surface, powered by nothing but gravity and time. If that life exists, it will not greet us with colorful reefs or towering chimneys. It will be subtle, tenacious, and unlike anything evolution has produced on Earth. It will force us to expand our definition of habitable, to accept that biology can be patient, hidden, and sustained by forces we barely understand.